Alright, so we're going to look at another example of a MOS amplifier design. And in this case, we have an amplifier shown in the schematic. We have the input coming in on the source of a PMOS transistor and the output coming out of the drain of the PMOS transistor. And this means that this is a common gate amplifier. So let's go ahead and see if we can draw the small signal model. In this case, the gate is grounded. We have our voltage-dependent current source. We have the output resistance or conductance of the device. We have the drain resistance. We shorted the big capacitors. And finally, we need to add our source resistance and our input. Okay, as we did before, we're going to solve this by using KVL and KCL on our model. We have a few things that we know right away. The output is actually equal to the drain voltage, and the input is equal to the source voltage. So we can write our first KCL expression starting at the output node. So we have VDS over R naught plus VD over RD plus GM VGS is equal to 0. Now here we're noting that G naught is equal to 1 over R naught, so we can use those interchangeably. After a little bit of algebra, you can show that this expression is equal to the following. So here we have the expression V naught times 1 over R naught plus 1 over RD is equal to VI times 1 over R naught plus GM. So interestingly here, we don't actually have to do any more nodes because we're ultimately going to try and get this in terms of V out over Vn, and we already have everything we need. So with a little bit more algebraic manipulation, you can show that V out over Vn is equal to 1 plus GM RO times RD divided by RO plus RE. And this is approximately equal to GM times RO RD over RO plus RD. Now, generally, we know that RO is much greater than RD. In other words, we can further approximate this and say that it's equal to GM times RD. Now, in the context that we've talked about before, the little gm in this case is actually equal to the big GM that we've been talking about. And the RD is actually equal to our RT. So we're going to stop there for this video. And in the next video, we're going to look at finding input and output resistances. In general, what we see is in order to find the gain of a MOS transistor, it's very similar to finding the gain of a BJT transistor. We need to draw our small signal model and do nodal analysis. What we're ultimately going towards, though, is if we identify that every common source amplifier or every common gate amplifier or every common drain amplifier follows the same form, hopefully we can find shortcuts to the analysis that allow us to find big GM and big RT without having to draw the small signal model. And we'll keep practicing on that.